Hello everyone. So welcome to IIT and Gate classes. So today we'll be continuing from the last session. So that's the part two of expansion waves. So let us jump on to the problem. So myself Akshay. So in the last session we saw about like how to obtain the properties across expansion waves. So whenever the flow is turning away from the flow direction. So how the properties will actually change whenever a supersonic flow turns away from the flow direction. And we did assume that the flow is isentropic. The other assumption we made is it goes through a series of Mach lines. So in today's session, we'll be digging more into the idea of this Mach lines. Why exactly is Mach lines, and can we show that it's indeed a Mach line? So that part we are going to see in the today's session. Okay, so let us come back to the geometry once again. Here you see I have a supersonic flow with M1 Mach number in the upstream, which is greater than 1, and which is seeing a gradual corner which is deflecting away from the flow direction. So in this scenario, one would expect that flow to accelerate. So this part we actually going into the details when we talk about intakes and or the supersonic nozzle or diffuser design. So when the flow is actually diverging, moving in a diverging section like this, so we see a supersonic flow will accelerate further in the diverging section. It's a little contrast to our low speed counterpart, where we have seen that if Mach number is less than 1, in the diffuser, the flow is actually decelerate. So we call it as a diffuser because the flow is decelerating. But when it comes to a supersonic flow, whenever the flow sees the diverging section, we see that a flow will accelerate. So that's what we will discuss once we again come back to nozzle flow. But here, this idea can slightly be taken here. Whenever the flow is diverging like this, it sees a diverging section like this. So it actually accelerates. So while doing so, what happens whenever the flow has to accelerate? So one would expect that static pressure to decrease, right? So if the static pressure is decreasing, that means velocity is also increasing. So that means like the pressure energy will be transformed into a kinetic energy kind of thing, right? So now we see here. So I'm defining a coordinate system for this now. So far we actually dealt with a Cartesian coordinate system. Now we will slightly move away from Cartesian coordinate system, and I will introduce you the polar coordinate system over here. So this is a radial direction R. So my coordinate system starts at the corner. So these lines are the Mach lines, whatever I have here. So that's we are going to prove it is actually Mach lines. So let us take it some radial lines. So in R direction. Okay, R is in this direction, and this angle, whatever I am measuring, I am denoting it to be phi direction. So the moment when I introduce this kind of coordinate system, so now I have to use the governing equation in this coordinate system. Okay, so before I introduce you the governing equation, let us slightly understand the geometry first. Okay, so let me take one radial line like this in the R direction, okay, which is at an angle phi from the reference system. So the vertical line is my reference system from where I am actually measuring angle phi. Fine. And we know that this Mach angle is always defined with respect to the flow direction and this radial line. So if I call it as a Mach line, then I will call it as actually Mach angle. Let us just define mu as a angle which is measured with respect to the radial component to the velocity direction itself, right? So this is my local velocity vector. So velocity is actually changing like this, right? So in this, if I take at any local point, so my velocity is gradually changing. So if I draw the tangent to this one, so this velocity vector v, the tangent to this curve, so this is my direction of velocity at that instant, at that location, right? Being its steady flow, so the instant part we are actually taking out. At this location, this is my velocity vector. With respect to this velocity vector, to the radial line, whatever angle I am having, I am calling it as mu. Let us stick to that one. We'll forget this one. So we will actually going to fluid. Okay. So now for this velocity, if I split in radial component, so this is my VR vector and this is my V5 vector in the phi direction, right? Okay. And with respect to my incoming flow, how much this velocity vector is deflected from the incoming flow direction as soon as it passes through this radial line. So this is my deflection angle theta. Fine. So if we understood this particular diagram well, now I can easily see. So this is always perpendicular to this one, VR and V5. So I can easily define sine mu, right? So sinusoidal of this angle mu is given by opposite to hypotenuse. So that is V5, that is this velocity component to the total velocity component V. Okay, so this part we understood pretty well. So now we will move on to introduce the governing equations, right? So what are the governing equations we are actually interested in? So of course we are interested in continuity equation and the momentum equation, right? So the continuity equation and momentum equation is a vector equation we have to remember. So we have to write it in two components of velocities. One is VR component and V5 component, and the other component we will treating it as azimuthally it is not changing, or in the other direction it's not changing. It's a 2D problem still. So two components of velocities corresponding to two momentum equations and one continuity equation, right? So let me call this as equation 1, equation 2 and equation 3. Now what I am actually assuming is, so we have to have some kind of a constraint that in the radial direction nothing changes. See, like I had a corner like this, right? So I had a corner like this and I had an expansion like this, radial line, right? So along this radial line, nothing changes. So from this point to this point, if you measure at any point, the properties will not change along the radial line, whereas it changes in phi direction. Let me call this is my phi direction. In this direction, flow properties changes, but in this direction, nothing changes. So that is the assumption we are going to take. It is a safe assumption because we can easily sense that nothing changes in the radial direction, but whereas when the flow passes through the gradual corner, so the properties will change in this direction. That's the assumption we are going to take, and it's actually a valid. But moment when I have this constraint, so my governing equations look so simple. Right now I have in polar coordinate with respect to r and with respect to phi. So these variables are defined. All these differential equations are defined with these two variables as a function. So now when I have a constraint like in the radial direction nothing changes, so all these derivatives with respect to radial component r is going to vanish. That means like dou VR by dou R or dou P by dou R, dou V phi by dou R. All these variables which are differentiated with respect to R are going to be 0. They are not varying. It means like I can actually put this is 0. If I expand this one, so I can have dou VR by dou R, that is going to be nullified. Even dou V phi by dou R, this is going to be 0. So that part we are going to see now. All right. So let us try to expand this equation a bit more carefully. So what I am going to do, so the continuity equation, so I am going to write in terms of, so I am going to split these variables in rho R times VR. So now what happens, so I can write like VR times, or yeah, VR times dou rho V, dou, I will get rho VR, dou by dou R of R plus R times dou of rho VR divided by dou R plus, let me keep like this, dou by dou phi of rho V phi equal to 0. So now we know in radial direction, this is not going to vary. So I can safely put this as 0, whereas dou R by dou R is nothing but it's just the differentiation with respect to the same variable. So it is going to be 1. Right? So my continuity equation looks like rho VR plus dou by dou phi of rho V phi equal to 0. So this is my modified continuity equation. Similarly, the R momentum equation, this part vanishes, this part vanishes. So I am left with V phi by R times dou V R by dou phi minus V phi square divided by R equal to 0. So I can take out R. So I can write in terms of V phi times dou V R divided by dou phi minus V phi equal to 0. So this is my R momentum equation. Or I can take out this V phi also. So I left with V phi is equal to dou V R divided by dou phi. This is very important intermediate result we will be using later, right? So I got what is V phi in terms of VR. Okay. Now I am using phi direction momentum equation. Here what I have, VR times dou V phi by dou R, right? So this part goes to 0 and okay. So now what I left with, if I take V phi common over here, V phi by R, or R we can cancel from all the sides because this term is already vanished. So I can easily take out R. So now what I left is V phi times dou V phi divided by dou phi plus VR is equal to minus 1 divided by rho times dou P by dou phi. Right? Now you look this equation very carefully. This differential equation is only a function of phi. With respect to phi, we are differentiating. So this partial differential equation now becomes like a ordinary differential equation. So I can easily write V phi times dV phi divided by d phi plus VR equal to minus 1 divided by rho times dp by d phi. So what is the advantage of representing any differential equation or reducing any differential equation into ordinary differential equation? Because it can be easily solvable. Partial differential equation is a bit difficult to solve, but the moment when I bring it to a ordinary differential equation form, so it becomes a solvable. Analytically, it can be approachable, right? So the another interesting part is, so now I can write dp by d phi in terms of, because we have to note that pressure is a function of density as well as the direction phi. So it is actually function of both. So I can write dp by d phi in terms of dp by d rho times d rho by d phi, right? So now I can write like this. And what is dp by d rho? So it should ring a bell, right? So dp by d rho, we already saw while discussing the speed of sound, right? The moment when I take this is changing isentropically, that means dp by d rho is nothing but speed of sound, right? So dp by d rho I can write in terms of speed of sound squared times d rho by d phi. So I am just using the definition of speed of sound, right? So now I am using this result into this phi momentum equation. I'm using that one. You see here. So this is where we got. So I'm using this result back to this equation where I have minus 1 by rho dp by d phi. So if I put over here, so what happens? A square times minus 1 by rho times dp by d phi. Right? So I am keeping that into that equation. So now what I am doing, so I am taking help from my R momentum equation. So we got a very beautiful result, that is nothing but v phi is equal to dvr divided by d phi. Again, I am writing in terms of ordinary differential form because it's only function of phi, right? So now from the phi momentum equation, what I had is v phi times dv phi divided by d phi plus vr equal to minus 1 divided by rho times a square times d rho by d phi. Right? So now if I represent this d rho by d phi in terms of all the other variables, so this becomes d rho by d phi is equal to minus rho times dv phi by d phi plus rho times vr times so v phi. Right. So from here I have v phi times dv phi divided by d phi plus vr equal to a square minus rho v phi times minus rho times, I'm replacing this d rho by d phi in terms of this variables, dv phi divided by d phi plus rho I already taken out, so it is just vr so now this row and this row get cancelled. So what I am left is v phi square. So I am taking this v phi to other side. Actually 1 divided by v phi. So this is going to be v phi square times vr plus dv phi divided by d phi is equal to minus of minus get cancelled, minus of minus, so it's plus now a square times dv phi divided by d phi plus vr. Okay, so I have a similar term, but I am not going to cancel this now because we have to see a very important result before cancelling out, right? So if I take common, so I get like vr plus dv phi by d phi times v phi square minus a square or a square minus v phi square, depending on whether you are taking LHS to RHS or RHS to LHS, it doesn't matter. But the thing is like we get a term like v phi square minus a square equal to 0. So now I have to decide which of these two quantities has to be 0 to become a valid expression, right? So if I put this term vr plus dv phi by d phi equal to 0, what happens? That results in dp by d phi going to 0. Why? Because if you see the phi momentum equation, what we had. So in the phi momentum equation, we had v phi times dv phi divided by d phi plus vr equal to minus 1 by rho times dp by d phi. So it is before splitting into dp by d phi into function of rho and phi, it's just dp by d phi, right? So if this term goes to 0, so this results in dp by d phi going to 0. But that is not valid, right? P is actually varying in phi direction, right? It's function of both density and the phi direction. So this is actually not a valid reason. That means if this equation to be valid, the only possible solution is this term to become 0. What happens if that term becomes 0? 1 minus v phi by a square equal to 0. So that results in v phi is equal to a. So we are getting very beautiful result over here. So if v phi becomes a, that means this velocity component is nothing but a local speed of sound. That's what it states. It's a very important result. It states that the tangential component of velocity is equal to the local speed of sound. This means a radial line should be a Mach line, right? So this is where we can actually show the proof that indeed those radial lines what we saw in the derivation of property change across the expansion waves, that is actually a Mach wave. So we have infinite number of Mach waves through which a flow is actually diverging. So even from mathematical point of view, this is shown, and physics also says that through that the flow is actually accelerating. And that is an isentropic flow. If that is not an isentropic flow, then we cannot get this result. So across the Mach wave, we already know that Mach lines are the limit to the shock waves where the properties will change such that the total pressure is not going to be lost, or we are not going to see an entropy increase. So the entropy stays constant. So that's a very important result for from physics point of view. As an engineering point of view also, it is very beautiful result. Whenever I have a gradual change, so I can expect a lesser total energy loss, or the entropy change, right? So you have to also remember this Prandtl-Meyer function is basically derived based on these assumptions that the property change in a supersonic flow happens across a gradual change. So irrespective of whether we are actually doing a diverging kind of uh, surface, or the flow is seeing a compression corner, even the gradual compression corner. So like this, say like this, where the flow has to go through a series of compression. So still we can get a expansion compression corners. So through which when the flow is going through, so these can result in constant entropy process. So that means even the compression can happen with the isentropic manner. It is actually possible, theoretically possible. Practically, we can design with a very minimal total pressure loss. But the problem with this design is it takes, like, in theory, it takes an infinite length of the compression corner to achieve a zero total pressure loss. So in practice, we have to have a very large intake designs kind of thing. So because we know the very practical application of this compression corner is to use in the supersonic or hypersonic intakes, where you have to have the ram effect, right, to the maximum effect. So I have a supersonic intake like that. So there will be an oblique shock wave, and there will be a very weak shock wave, normal shock wave, and the compression will happen such that the series of the flow will go through a series of compression corners, and then the compression will happen so that the fuel can burn at the proper pressure. But in theory, we can design this kind of a compression where it goes through compression with no pressure loss, no total pressure loss at all, or no entropy change at all. But in practice, if I want to design a Prandtl-Meyer kind of an intake, then I have to have this length of the intake, which is very, very large. So it's practically not that feasible. So that is why people will not go into the details of that one. But it is interesting. So it is an active research area where people are trying to understand the curved RAM or curved intake design. Okay, so this was the part I really wanted to discuss in detail. So that is why. So I kept it as a separate session. I hope this answers some of the doubts regarding, like, why we are actually considering the Mach lines. Why not the oblique shock kind of thing, right? Okay. So now the moment when I have V5, which is equal to A, speed of sound. So if I go back to my geometry again, we define this angle mu as sine mu is V5 divided by local velocity V. So that means sine mu is V5 divided by V, or which is equal to A divided by V, or which is equal to 1 divided by V by A. So what is this one? This is nothing but the Mach number, right? 1 divided by Mach number. So this is the definition of a Mach angle we defined in the very beginning of the session, right? So that means this is nothing but a Mach angle, or this line, radial line, is nothing but a Mach wave. So that's what we proved. Okay, so let us take some questions from previous year gate, from expansion wave. Okay, so this question is asked in 2017 gate. So they asked that a trace from the Schlieren photograph of the flow around a corner reveals the edges of the expansion fan as shown below. The leading and the trailing edges of the expansion fan makes an angle as shown. Assuming gamma to be 1.4, the angle of the expansion fan in degrees is. So they are asked you to keep your answer in 2 decimal places. So keep in mind, like while reading the question, please also take note of these key points. So what they are actually asking, and in how many decimal places they want you to put in and all. So these are the parts you have to practice. Okay. So they also given Prandtl-Meyer function. So the functional form of Prandtl-Meyer function is given to you as a function of Mach number and gamma, right? So now you see they have given the figure. So this is an image from some experiment. So where they have captured this expansion fan, where they could actually recognize what is the starting Mach wave and what is the last Mach wave. So what you can do is, so you have a 143 degree from this surface. So that means if I extend this line, right? So flow direction is parallel to this surface. So to the flow direction, this is my Mach angle mu1. So if I want to calculate mu1, that is going to be 180 minus 143 degree is nothing but mu. So that is going to be 37 degree, right? So I got my mu1. We call it as, let us call it as mu1. And mu2 is already given to you with respect to this flow direction. So whatever the angle is, this last Mach line is making, that is mu2. So mu2 is 20 degree given in the figure, right? So all they are asking you to calculate the angle between this point to this point. So that is the starting Mach wave to the final Mach wave. So this is the expansion fan wave angle. So expansion fan angle, let us denote it as phi. So this is what we have to determine. So how are we going to approach? So it's a straightforward. From the geometry, we already understood that the only missing part over here is the theta, the deflection of this one. So this theta is unknown. We don't know. But we have a very beautiful relation from the Prandtl-Meyer function that theta can be written in terms of mu of m2 minus mu of m1, right? So Prandtl-Meyer function at Mach 2 minus Prandtl-Meyer function at m1 will give you the deflection angle theta. So since this functional form is given to you, so you can directly put these values over there to get the Prandtl-Meyer function. But the thing here is, like, we really don't know what is this Mach number 1 and Mach number 2. But how can we calculate that? Again, it's a straightforward, because those two are Mach lines. So I can use sine mu1 is equal to 1 over m1. So from here, I can actually calculate m1, that is equal to 1 over sine mu1. So mu1 is 37 degree. If I use that one, so I should get m1 to be equal to 1.66. If you want to put, you can put more digits, it's fine. 164. Similarly, what is m2? M2 is nothing but 1 over sine of mu2. So if you put that one, so mu2 is 20 degrees. So if you put that one, so you should be able to get m2 to be 2.9238. Okay. So now I got what is m1 and what is m2. So now use the Prandtl-Meyer function. So we have v of m is given by root of gamma plus 1 divided by gamma minus 1 times tan inverse of square root of gamma minus 1 divided by gamma plus 1 times m square minus 1 minus tan inverse of square root of m square minus 1. So this is the Prandtl-Meyer function we have. So if you keep m1 equal to 1.66, so I will get mu of m1 to be equal to 16.69. Similarly, if I put m2 in this expression, so I will get mu of m2 as 2.9238. So I will get mu of m2 to be equal to something around 48.26. $48.2635, something like that. 26535. Okay, fine. You can write 27. So now my theta, the deflection angle theta, is nothing but mu of m2 minus mu of m1. So that comes out to be 31.574 degrees. 4 degrees. So now I can easily calculate what is expansion fan angle. So that is phi. So from the geometry, I can easily show that what is phi. So let us just go back to the geometry again. What is phi? That is mu1 plus mu2, mu1 plus theta minus mu2. So that's what phi, right? Mu1 plus theta minus mu2. So that is phi. So you use that one. Mu1 plus theta minus mu2. So theta is 31.574, mu1 is 37 plus 31.574 minus 20. So you should get phi is equal to 48.57. So they asked you to put in 2 decimals, so I am just keeping it in 2 decimals, 48.57 degrees. I can keep that as the answer. Okay. We also had one more question. So that is from GATE 2013. So here the question is asked in different way. That means the data is presented in different way. So it's the same idea, but the data is presented differently. So in the last case, they are given this clear in shadow graph kind of idea where they are given the geometry and from where you can make out. So in this case, they are actually given for different Mach numbers what is the corresponding Prandtl-Meyer function. So they are not asked you to calculate actual Prandtl-Meyer function from the formula. So they are given the values for different Mach numbers. So from here you have to judge what should be the downstream Mach number in the expansion fan. So let us read out the question carefully. Consider a supersonic stream at a Mach number m2 undergoing a gradual expansion. The stream is turned by an angle of 3 degrees due to the expansion. The following data is given. The Mach number downstream of the expansion is. So straight away what you can do, whatever is there above 2 is not needed for us. So because it is going to a gradual expansion, so that means it's accelerating. So I am expecting an expansion wave, right, like this. And so they are given this angle, the deflection angle is theta equal to 3 degrees. So that is the deflection angle turned by an angle 3 degrees due to the expansion that given. So this is my upstream direction, M1 equal to 2. Fine. So now what they are asking you to calculate is what is the Mach number behind the expansion fan? What is M2? That is what we have to find out. So how are we going to approach this problem? Again, idea is similar. So first we will try to get whatever is known to us, right? So from the given information, what I can calculate, theta is given by mu of M2 minus mu of M1, right? For M1 is equal to 2 degree, so mu of M1 is 26.38. So theta is 3 degree. So I can calculate mu of M2 to be equal to theta plus mu of M1. So that is nothing but 3 plus 26.38. So that is going to be 29.38. So if I get this value, so corresponding to this one, what should be the Mach number? So let us look at the table very carefully. So I have 26.38. This is 29.38. So I have 29.10. I have 31.73. So that means if mu of, like you see, mu of M1 is increasing with respect to M. So with the increase in Mach number, this is also increasing. That means it has to fall somewhere between 29.10 and 31.73. It cannot go beyond this. So this is not needed. So this is already used. So now I should have an answer which is between these two values. But if you see the given option, this one I can easily nullify. No use. This is also not used. This is also greater than that one, 2.33, that is 34.28, 2.3 plus that one. So this is not. So by elimination method, you can easily choose option C as an answer, but still we will find out. So what if it is asked in the numerical entry type? So we will find out. So we can actually show that. But here what I am using is like I am slightly doing the extrapolation. So for 2.1, for M2 is equal to 2.1, I have mu of M2 equal to 29.1, right? 29.10. For 2.2, for M2 is equal to 2.2, I have mu of M2 is equal to 31.73. So I'm just doing the extrapolation, doing the linear fit. So that is nothing but y2 minus y1 divided by x2 minus x1 equal to y2 minus y divided by x2 minus x kind of idea, linear fit. So if I have a curve as mu of m and m, a function, if it is fitting linearly, so if I want to find out the slope, so this is how I use, right, the 2-point formula. So that's what I'm using now. So in this case, I have 2.1 minus 2.2 divided by 29.1 minus 31.73 should be equal to 2.1 minus unknown Mach number M2 divided by, so corresponding to 2.1 I have 29.1 minus, so we calculated mu of M2 from our problem, that is 29.38. We keep that one, 29.38. So if you solve this equation, so it is straightforward to show that, so M is equal to 2.1. So you can try it by yourself. So I'm just giving you the method. Okay. So this concludes our discussion on expansion fans. Okay. So thank you for attending this session. So if you have any more doubts, so you can reach out at IIT Engage classes. Thank you.